Let's talk about free fall and not free fall, aka air resistance. Under what circumstances is it safe to use the 5 equations of motion that you took down in physics class, and under what circumstances is that not really going to be an accurate model of what's going on in the real world? Free fall we've been studying for days. It means gravity is the only force that's taking care of the object the instant that it's left your hand. You're not telekinetic. It has no engines, no wings, no parachutes, no wind, no any kind of resistance or outside forces of any kind. Gravity is constant, acceleration is constant, and this gives us the 9.81 meters per second downward that we measured in the lab, aka the value of negative 9.81 meters per second squared that we've been using for days. Review. After the ball's left your hand, it goes with an initial velocity of VI, with a velocity of 0 at the top, and a final velocity of VF the instant before it begins to land. We're not going to do after it lands until we're ready to study collisions. But remember, what goes up must come down. The instant after you let go, gravity is in control, negative 9.81 meters per second squared. At the top of the path, gravity is still in control. That ball is going to go down, negative 9.81 meters per second squared, until it actually is in the process of hitting the ground. That 9.81 meters per second squared down is in control the entire time. Gravity is constant, so your acceleration is constant. Constant gravity, constant acceleration. Let's talk about air resistance that interferes with gravity. The drag force is a second separate force. Free fall is no longer free of outside interference. Now we've got 2 forces. The drag force builds up over the fall. The more fall you have, the more drag force there's going to be, and that means the object does not pick up as much speed as expected. And eventually, after a certain amount of time, the object no longer picks up any more speed at all. Get this, air resistance does not slow you down. I will say it again, air resistance does not slow you down. Air resistance prevents you from speeding up as much as you would have otherwise. It's not that you get fast and then you go slow. It's that you never go that fast to begin with. After a certain amount of time, you max out and you will go at the same speed the whole time. If you're a parachute jumper, you want that time to be sooner rather than later so that you pick up very little speed on your way down. Check it out. In free fall, if you toss a perfect ball off a roof, it'll fall and it'll fall and it'll fall and it'll fall, and about 2 seconds later it'll hit the ground, and that'll be all fine and dandy. And when it falls, it'll pick up speed and pick up speed and pick up speed and pick up speed, and it'll keep on picking up speed forever because gravity is constant, and gravity is the only force controlling the ball's motion after you drop it. But if it's a real ball falling through air, you'll notice that the air drag curve is very different than the free fall. It falls more slowly. It doesn't go as far, and it takes longer to hit the ground. Why? Because you're not picking up speed the whole time. You're picking up speed maybe in the first half second, but at the first half second or so, you're not picking up as much speed, and by 2 seconds, you've picked up all the speed that you're going to have. The word for this is terminal velocity, but don't use that phrase in my first year physics class because we're more concerned with controlling it than getting all excited about the fact that it has a name. Take a look, the acceleration is no longer constant. The acceleration starts at negative 9.81, sure, but all that air resistance means you can't pick up as much speed anymore. By the end here, you're hardly accelerating at all. Now, the big one, put a huge box around this portion of today's notes. This is what you're going to be using for design projects for the rest of the year. Air drag, according to the experiments we did in class, depends on cross-sectional surface area, mass, shape, which is basically if you're streamlined or not, and velocity. Write those down, put a box around them. These are things that we wish to control. Now, cross-sectional area isn't surface area per se. The surface area of this marker would be a sort of rectangle here and a circle here and another circle there. What we want is the cross-sectional area, namely the area that's facing the relevant direction. If you were a car, whoosh, the relevant direction would be horizontal. But given that we're doing this to try to determine when we can and cannot use freefall, when the relevant direction is down, the cross-sectional area looks like this because this is the part of the marker that's facing down. Cross-sectional area can be controlled by shape. It can also be controlled by technology. Pause and think for a minute. If you wanted to control your cross-sectional area in order to fall a lot more slowly, not slow down, but never pick up that much speed to begin with, what would you wear? Press play when you're ready. That's right, you would wear a parachute. A parachute would mean that you don't have a cross-sectional area like those skydivers, sort of body outline all spread out. Your cross-sectional area is a giant rectangle. It's huge. Important fact that came up in the lab: surface area and mass are not completely independent. That is, if you put on a parachute, it's not going to do you a whole lot of good if the parachute is so heavy it gives you tons of mass. You want to increase your cross-sectional surface area from this to this without increasing the mass. You want a higher surface area to mass ratio, with higher surface area meeting a lower mass. Speaking of mass, this is a common misattribution wrongly attributed to gravity. True or false? Heavy objects form more quickly. Well, on Earth, technically it's true. Try the old drop an apple in a feather or drop a hammer in a feather. Try it now. Try it with a pencil and a piece of paper. You will see that clearly the heavy object falls more quickly. But this isn't gravity. It's not that the heavy object falls more quickly. It's that the lighter object has more air resistance and therefore doesn't fall as quickly. It falls more slowly because it hasn't been picking up as much speed. If you have less mass, you're going to have more air resistance. This is the denominator in the surface area to mass ratio. You want to have less mass without necessarily increasing your surface area. You want a high surface area and a low mass if you want the air resistance to keep you from going too fast. Now let's talk about streamlining. Streamlining is putting the air in air drag. The whole point of air resistance is that the air resists you. You're cutting through it. The two kinds of airflow are laminar flow, which is as close to linear as anything's really going to get, and turbulent flow. Anybody who's ever been on an airplane, turbulence, a bad thing or a good thing? That's right, it's a bad thing. It's shaking you up all over the place, and nobody is going to move well or easily through turbulent air. Turbulent air is going to have a whole lot of air resistance. Shape is a factor in as much as it tells you how the object is going to cut through the air. Let's take a look at the animations. This is normal airflow, and you can see as you change the angle of the wing, you'll get a whole lot more turbulence, and that is going to increase air resistance. Thank you very much to the web programmers who have these wing simulations for aerospace engineers. Apparently one of them had an awful lot of time on her hands, and she did an aerodynamic simulation of a cheeseburger, which is designed for many things, but aerodynamics not among them. You can see the way the turbulence builds up behind this shape, which isn't really meant to cut through the air. If you want to minimize air resistance, streamline. If you want to maximize air resistance, don't streamline. The final variable here is speed. Speed is the most important variable we have in terms of air resistance. This is the source of the common misconception that if you drop something off a much higher roof, the extra drop height is going to give you more air resistance. No, it's not the drop height. It's not even the longer air time. Push your pencil and a piece of paper off the desk, then stand on your chair and try dropping the pencil and the piece of paper. You'll see you get a lot more air resistance, but it's not because of the longer fall time. It's because having a higher drop and a longer time gives you the ability to build up more speed. And this factor can completely dwarf any advantages given by the others, because this is a car that's designed to break the sound barrier. It is streamlined. It has as low a mass as possible under the circumstances, as a minimum cross-sectional area, and yet it still builds up tremendous air resistance because it's going at such a fast speed. This is the big one. This is the one you can't necessarily control. Higher speed isn't just more air resistance. Higher speed is a lot more air resistance. Review: how to minimize air resistance and be as close to free fall as possible. Write down 3 things. Go on, pause the video, write it down, and then add in one silly one for how to absolutely minimize air resistance. Go. Ready for the conclusions? Minimize air resistance. You want a small surface area to mass ratio. That is, you want a low surface area compared to a higher mass. Streamline as much as possible to minimize turbulence, and go at as low a speed as possible, but given that the whole point of minimizing air resistance is so you can go very, very, very fast, this is kind of ridiculous advice. Honestly, if you want to minimize air resistance, go to outer space. No air, no problem. Now, the opposite. Make the opposite list under maximizing air resistance. List everything you can do to take full advantage of your air resistance. Ready? Go on. Press play when you're ready. All right, let's see. We want a huge surface area, as low a mass as possible given that we have to carry a parachute. We want as high a speed as possible, and this is why on Star Trek Reboot, when they're jumping from the top of the atmosphere to disable the bad guy's evil device, they don't deploy their chutes the instant they're clear of the ship. All right, everybody knows don't deploy your parachute so quickly that you get stuck in the airplane. Nice bit of physics here. Sound does not travel in space. But after they've had their nice long fall and it's time to deploy, you're going to notice that they wait until they're going insanely fast to open their parachutes, because the parachute won't be good for much until you're going a very high speed to begin with. Here's a quick preview of the equation that you're going to see next year in AP Physics. Bad news, there are multiple models of the drag force, and the only way you can figure out what kind of drag force you're working with is to go to the wind tunnel under the engineering building and test it. One model of the drag force, the simplest one, says the drag force depends on your velocity, it resists your motion, and it's basically dependent on a whole bunch of things, including your surface area and like other stuff, don't you know? So Newton's second law, mass times acceleration. Let's pretend this is the only force you have, and if it is, you'll see that your acceleration depends on going at high speed, having a nice large surface area and a small mass. There's your surface area to mass ratio. All right, it doesn't look like a surface area to mass ratio, I know. Well, that's where the more complicated model comes in. The more complicated model, such as the AP Physics class measures in the lab when they use the common coffee filter, the only object in our building whose drag force is simple enough to measure it in a pretty equation like that. Well, that drag force depends on a lot of stuff. It depends on CD, the drag coefficient. This is the result of all that extreme calculus for your streamlining. Streamline has a low drag coefficient. A cylinder with a cross-section of a circle has a much higher drag coefficient, but not as high as a square. Rho is the density of the air, taken into account the chemical composition of the air, the humidity, the temperature, all that stuff that could make air thicker and harder to cut through, or thinner and easier to cut through. There's your A for cross-sectional area. And there is your surface area to mass ratio that we were talking about before, depending on the square of the speed, which is why if you double your speed, you don't get twice as much air resistance. You get 4 times as much air resistance. 10 times the speed will give you 10 times as much air resistance. Sorry, will give you 100 times as much air resistance compared to 10 times the area, which would only give you 10 times as much air resistance. All of this is assuming, of course, that you've got no gravity and that the drag force is the only force going on here. Not a safe assumption given that we're working with freefall. Once you have gravity in, it's only a mid-level differential equation of the first order that probably requires a year and a half of calculus before you can solve it. And then things get more complicated from there. That's why in first year physics, we rely on design principles and engineering techniques to look at air drag. If you've got a small surface area per a very high mass, you're trying to streamline and you're not jumping off the Empire State Building on the end of a bungee cord, then you can approximate that, you'll probably be in free fall. But if you have a very large surface area compared to a smaller mass, you're spread eagled instead of streamlining, and you're going at a high speed, going whee, then there's no point in busting out the 5 equations of motion, because air drag is going to have more to do with how fast you're going and where you end up than simple free fall.